So the last question of week 5 tutorial is going to be about the cutting temperature. So the same question we had earlier, we do have the cutting operation. We have the alpha value is 10 degree or the rectangle, 10 degree. We do have the value for the initial thickness of the chip is 0.5 millimeters. The final cut thickness is 1.125 millimeters. During the cutting force was found to be 1,559 Newton, and the thrust force was 1,271 Newton. The width of the orthogonal cutting operation was 3 millimeters. In addition, we had the volumetric specific heat for the work materials was 3 multiplied by 10 up to the power minus 3 joule per cubic millimeter degree, and the thermal diffusivity given as 50 multiplied by 10 up to the power minus 6 meters squared per second, or 50 millimeters squared per second. So by now we know the shear plane angle and the shear strain of the operation. We know the shear strength and of the work materials. We know the friction angle and the coefficient of friction. And we calculate the cutting power and the specific energy in the machining operation when the cutting speed was 100 meters per minute. Now we need to know what will be the increase in the temperature above the ambient temperature of 20 degrees. So we need to know about the cutting temperature. When we are going to have a cutting operation, you will see that the part is going to get too hot. Approximately 90% of the energy in the machine is going to be converted into a heat. And this can cause the temperature to be very high at the tool tip, and you can see it's going to be glow red. The remaining energy, or about 22%, is going to be retained as the elastic energy in the chip. That's why you can see that the chip shape is going to be changed as it's going to be leave the part. So the values for the unit horsepower and the specific energy for the selected work materials using the sharp cutting tool and the chip thickness before the cut to be 0.25 millimeters are given in the following table. So what is the cutting materials we have, what the cutting materials and the Brinell hardness for them, and the value for the U in case of the SI unit or the IP units. Okay, so the high temperature usually going to have negative effects on the machining operation because it's going to reduce the tool life and also going to produce a hot chip that pose a safety hazard to the machine operator, and also can cause the inequalities in the part dimension due to the thermal expansion of the work materials. So we're using an analytical method derived by Nathan Cook from a dimensional analysis using experimental data for various work. And this equation tells us that the change in the temperature is going to be equal to 0.4 multiplied by the specific energy divided by the volumetric specific heat of the work materials multiplied by the cutting velocity times the chip thickness before the cut divided by the thermal diffusivity up to power 0.333. So let's see how we can apply this equation to find the change in the temperature. So let's read the question once again. What we need to apply Nathan equation or Cook equation is going to be the TO value is given here. We are going to need to find the volumetric specific heat, or the rho C of the equation is given here. We need to find the value of the thermal diffusivity, and it's given here. The U value has been calculated in the previous equation to be 1.039, and we're going to use that directly here. The cutting speed is 100 meters per minute. This is also going to be used. So the cutting speed must be converted to a millimeter per second because the U and the rho C use millimeter units. Thus, we're going to have that the cutting velocity is going to be equal to 100 meters per minute multiplied by 1000 millimeter per meter divided by 60 seconds per minute. And this will give me that the value is going to be 1,667 millimeter per second. And then we're going to find the mean temperature raise by calculation using the delta T equation from Aiken-Cook. The U we said is known, the rho C is known, the V now is calculated, the TO is given, and the K is given. So this is the K value we're going to choose because we're going to use the 50 millimeter squared per second because we're here using millimeter per second for the velocity, and we're going to use the T value to be also in millimeters. The U was given as 1.309. Sorry, the units are not watt, but anyway, I'm going to keep it like that because this will be watt over cubic millimeters. Okay, and the value for the rho C is going to be equal to 3 multiplied by 10 up to the power minus 3 joule per cubic millimeter second. Remember that this one, once again, is joule over cubic millimeters. So we're going to get rid of the millimeters directly. So now put everything in the equation, start the processing, and we're going to end up that the raise in the temperature is going to be 353 centigrade degree. Okay, thank you very much, and we're going to continue the rest of the questions as soon as we can.